Let's start with the third problem solving session. This week includes uncertainty analysis, zero order system, and first order system responses. So I prepared some problems regarding those. So initial starting one is a step input signal. So you have options. It's asked what is a step input signal basically. A step input signal is option A, starts from 0 and rises uniformly with time. So it says you have a 0, you have an input. Okay. So you have a 0, from 0 it uniformly rises, so it's kind of a linear, and then it says changes rapidly with time. So with respect to time it varies, step input signal, and start it varies rapidly, so it can be anything. Then C, starts from 0, rises to a particular value and returns back to 0. So it's basically like a rectangle or something like that, which rises and then falls back to 0. And then starts from 0, rises to a definite value in 0 time. So step input signal is starts from 0 and rises uniformly with time, changes rapidly with time, starts from 0, rises to a particular value and returns back to 0, starts from 0, rises to a definite value in time, 0 time. So the answer is D. So step input is when you input signal is at 0 time it rises to a value and remains constant. That is called a step input signal. Example is you have a beaker with a hot water, you want to measure temperature. So when you put your temperature measuring instrument, so it the temperature suddenly from the room ambient temperature to the beaker's temperature, you get that signal. So that is the sudden change, and that is a step input. It can be anything, loading it. So if you get a sudden value change, that is a step input signal, and with that remains constant throughout time. So answer D. And then the next question, it says a zero order system is the one in which output changes instantaneously as the input changes. So it's asking, it's saying a zero order system is one where the output and input changes with respect to time instantaneously. So it's asking for an example of a zero order system. The options are potentiometer, liquid in glass thermometer, accelerometer, and thermocouples. So we have to find out which is a zero order system. So if you remember, zero order system is Q naught equals KQI. So with respect to input, your output also varies and it's instantaneous. It doesn't take time to respond to the input. So if you vary your input, your output also varies at the same time. So out of the four, A, potentiometer, B is liquid in glass thermometer, C is accelerometer, D is thermocouples. So out of this, a zero order system is A, potentiometer. If you see, A is a zero order system where potentiometer is basically you vary the resistance with respect, and it can be a coil winding where you change the length of the windings so that the resistance of that part with respect to varying the length, you change the resistance, and that resistance in effect changes the voltage or current. So it will be instantaneous. So that is potentiometer. It changes the output. It will vary instantaneously when you change the resistance. So this is the first order zero order system. And then you have liquid in glass thermometer and thermocouples, accelerometers are first order system where you take time to respond to the input. Right, it will not be a sudden response, but it will take some time to respond and reach to an output value. And then moving on to the next question, we have the speed of a response of a first order system is judged by. four options. You have a first order system. So how fast the system response is, it's judged by out of 4. You have time constant, B is transient response, C is steady state value, D is rise time. So how do we judge a first order system? So the answer is A, time constant. The If you have a if you for example, if it's a thermocouple or which is as used for measuring a temperature, so that it will take some time to respond, but the t equals to t star, that is the one where it will be 62.7% there where the steady state value has been reached. So that is the time constant, and the others are, if you see, transient response is with respect to time, the variation, that is what is the transient response. The steady state value is what the temperature reaches, or the instrument, the value which has to be measured. So that steady state, what that has nothing to do with the response with respect to time. So and then you have rise time. Rise time is the total time it takes. So that, and so to gauge how fast the first order system is, the response is defined by the time constant. Then next you have the time required for the output of a transducer to rise to 63.2% of its final value when there is a step change in the measurand is called A, rise time, B, response time, C, settling time, D is time constant. So I have already told this. So the question is the time required for the output of a transducer to rise to 63.2% of its final value when there is a step change in the measurand is called A, rise time, B, response time, C, settling time, and D, time constant. So the answer for this is D, time constant. The largest change in the measurand value, if you see in this previous case, you have, for suppose if you take the thermocouple example, you have a temperature bath at some temperature T, and you have at the thermocouple is at room temperature. The maximum temperature it can reach is the T, then the fluid temperature, which has to be measured. So you write as theta by theta naught, where theta is the temperature difference between the thermocouple and the fluid, which is will be equal to e raised to power minus t by t star. So the response time, if which is to reach 63 point, is it should equal to time constant. So it will be t equals to t star. So it will be e raised to 1. So that will give you 36.8. So the difference will be the temperature would reach 63.2% of the fluid temperature at t equals to t star. So that's what this means. So the answer is option D, time constant. Moving on to the next question. The largest change in the measured variables which produces no instrument response is called. The largest change in the measured variable which produces no instrument response is called A, deadband, B, dynamic error, C, fidelity, D, threshold. So the largest change in the measured variable, you are measuring a variable and it produces no instrument response, that is called. So the answer for this is A, deadband. So where if you input varies and the instrument doesn't respond, it will take some time to respond. So that is called the deadband. Uh, so that's the answer here. If you see the next error, dynamic error is the error which varies with respect to time. Your input varies, and the input is your true value. For the input, you have some true value, and the instrument which shows for corresponding to the time, that will be the dynamic error. See, if you see fidelity, fidelity is a degree to which a measuring instrument is capable to reproduce the same value when the input varies. And it should not have any dynamic error. So the capability of it being reproducing the value is called fidelity. And D is threshold, is when the input you change the input and the initial amount of input for which there will be no output which will show. So after some input value is reached, it will start showing an output. So that is called the threshold. When the threshold is crossed, it will start responding. So initially, for some values, even if you give input, it will not show output. So initial, that is called threshold. If you remember, threshold and response are kind of similar. Response is the minimum input we require to show that output. It can be the least count, that is response, and the threshold happens at the start of the instrument. Moving on to the next question. The water discharge over a triangular wave varies as h raised to power 2.5, where h is the head above the wave. If uncertainty in the head h reading is 2% of the absolute value, what is the percentage error in disk air measurement? No error results in the measurement of the other quantities. So you have a water discharge over a triangular wave. The discharge is varying as h raised proportional to h raised to 2.5. So you can assume q is k times or constant c times h raised to power 2.5. If the uncertainty of the head, we are saying the uncertainty of head is 2% of the absolute value. What is the percentage error in discharge? It's not disk here, it's discharge measurement. No error results in the measurement of other quantities. So yeah, options 5%, 5.5%, C 6%, D 6.5%. The water discharges over a triangular wave. So you have uncertainty of h and the relation for discharge and h, how it varies. So the answer for this is a 5%. We'll see how we get. So we know q discharge is q, and then it's some constant times k into h raised to power 2.5. H is the head. So if you see from uncertainty analysis, you know uncertainty of q is root over or 2q of dou q by dou h into uncertainty of h the whole square. As this is a function of only h, so you have only one term of h. So from this, you know dou q by dou h is 2.5 times into k into h raised to power minus 1.5. So we know that error is 2% of absolute value. So error will be 0.02 h. So it's because 2% of h value, so 0.02 h. Then we know from error, this is for q is 2.5 k into 1.5. This is not eh, this is eq. So root over dou q by dou h is 2.5 into kh 1.5 into 0.02 h the whole square. So the error in uncertainty in q is 0.05 kh 2.5. So this is the uncertainty value for the discharge. So when you see the in percentage, it's 0.05 k h raised to 2.5, which we got then by q is kh 2.5, so into 100 we'll get 5%. So you have 5% error for uh, uh, your q discharge. And if you see, your head is 2%, as this is a relation of 2.5, this is varying by 5%. So moving on to the next question, we have discharge coefficient CD of an obstruction flow meter. You have CD is the discharge coefficient, and you have obstruction flow meter. Obstruction flow meter can be your orifice or something. So can be found by collecting the water that flows through it during a time interval t. So obstruction flow meter can be found by collecting the water that flows through it during a time interval t, which is in under constant head. So you have constant head under between the flow meter, which is head h, and then the relation prescribing the discharge coefficient is, so you have a relation given for the discharge coefficient, which is mass flow rate divided by for the time interval t. So this mass flow rate m by t is mass flow rate, so m by t into rho density into area of cross section, which through it flows, divided by 2gh. Say rho a 2g root of v root of 2gs is velocity basically, and that is m by m, mass flow rate by mass flow rate. So that is CD. So A is given, area is pi by 4 d square. D is the flow meter, the pipe in which the flow meter, the diameter of that. So and you have following data which has been given for mass flow meter. Mass flow is 400 kg plus or minus 0.25 kg. So that's your uncertainty, and then time is 600 plus or minus 2 seconds. Then h is 3.65 plus or minus 0.03 meter. Then g is 9.807 plus or minus 0.1 meter per second square. P is 1000 plus or minus 0.1 kg per meter cube. D is 1.25 plus or minus 0.025 centimeter. So you know the relation for CD, and you know mass, temperature, mass, time, and head, then G acceleration due to gravity, then P, then D, diameter, pressure and diameter. So you know the relation. The question is, you have to find the percentage uncertainty in CD when uncertainties are absolute values. So you have to find percentage uncertainty in CD when the uncertainties are in absolute values. You have values all given. So the option is 0.99, 1.01, C 0.97, and 1.03. Hint is, to solve this by uncertainty analysis, you know the product rule. You have to use the product rule. If some function f is x raised to power a plus into x raised to power a2, so on, so you will get a1 by uncertainty by x equals to the uncertainty which has to be found by the function value. This is square and root of the uncertainties. So the solution goes like this. You know area, which is pi by 4 d square. So if we find the diameter, which is given 1.25 centimeter, so we substitute that and you get 1.23 into 10 power minus 4 meter square. That's the area. Then CD for that corresponding case, where every value for every variable which is given, mass flow rate 400 times 600 into rho 1000 into area 1.23 in 10 power minus 4, and then 2 into g into h. So in that case you will get CD as 0.641. When the specified uncertainties are of absolute values, you can find the values. If you see the relation, you have to use the product rule relation. So dou m by m, you get a by uncertainty by the variable x. So that in that case you have uncertainty a is all 1. So dou m by m is 0.25. You have to find d uncertainty by the variable. So we are finding uncertainty by variable. In this case, starting with mass flow. So uncertainty by m is plus or minus 0.25 by 400. See, mass flow uncertainty is 400 plus or minus 0.25. So you have 0.25 by 400. Then for time, you start uncertainty by time. So it's a 2 by 600, which is 0.0033. Then for you have density. So uncertainty by dou rho by rho, which is plus or minus 0.1%. So it's 0.001. And then uncertainty for diameter. For in case of area, you have to find uncertainty from diameter is 0.002. If you see differentiate area with respect to time, we get dou A by A is 2 times change in diameter phi diameter. So the area is twice the diameter uncertainty by t. So plus or minus 0.004. Then with respect to acceleration due to gravity, you see you get plus or minus 0.1%. So it's 0.001. And same with respect to head, we know the values for head uncertainty and head. So it's 0.00082. Then the relative error in discharge coefficient will be dose. You have to find dose CD by CD value. We know CD value, which has been already calculated, and then the summation of that with the coefficients, which x the product how if it's h is h per half, so you can use that and substitute. On substitution, you get dou C by d by dou CD is 0.00987. So the absolute error in this case is you multiply with this with respect to the discharge coefficient. So discharge coefficient is 60.1% or 0.641. So if you multiply 0.00987 into CD, so in that case you will get plus or minus 0.00632. So the uncertainty in the discharge coefficient is 0.00632. So if you see in this case, this in percent, so we will have 0.00632 by 0.641 into 100. It's 0.986%. So if you see option, you have all values, and so the answer is A, which is close to 0.99. So the answer we got is 0.986. So the answer is 0.99. So the question is same to the previous one. It's a linked question. So in this case, we have asked been to find the uncertainty in CD when uncertainties are within plus or minus 3 sigma statistical limits. So when these are in statistical limits, we have to find the CD. And going back, we know the CD relation is m by t rho A root of 2gh, and area is pi by 4 into d square. So options 0.54%, 0.64%, then 0.59% and 0.69%. So moving on to the solution, we know when specified uncertainties are within statistical limits, we know the CD relation from the question. You have m by t rho A root of 2gh, and area we can substitute by pi by 4 d square. On substitution, you get m by pi by 4 d square into t rho root of 2gh. So now differentiate this with respect to each of the variables. So CD is function of mass, temperature, density, diameter, g, and acceleration due to gravity, and head. So starting with the one of the variable mass, so dou CD by dou m is 1 by pi by 4 t. The denominator term it will remain as it is. So the next, when you differentiate with respect to time, it will become m by pi by 4 rho d square root of 2gh. Time is 1 by t, so differentiate of that is minus 1 by t square. Then with respect to rho, you have m by pi by 4 t d square root of 2gh will be minus 1 by rho square. Then please note it will be minus 1 by rho square, and dou CD by dou D with respect to diameter is m by pi by 4 t rho into root of 2gh will be t is minus 2, so minus 2 d cube minus 2 by d cube, and dou c d by dou g will be m by pi by 4 t rho d square into root of 2gh. So g is minus half, so we'll have minus half into 1 by g raised to power 3 by 2. Same for head, you will get the same instead of g will be h. The uncertainty discharge coefficients are computed from the previous equation. So from uncertainty analysis, it will be a summation of uncertainty, the fractions differentiation of with respect to variable. So dou CD by the variable into the variable uncertainty whole square, the summation of all that raised to power 1 by 2, the square root of that. So we know from this when we take common CD and then differentiate divide it by that, so you will have em by m square. So it can be simplified as the below. So dou CD by dou m into uncertainty of mass flow, the whole square will become uncertainty of mass by mass the whole square plus uncertainty of temperature by temperature the whole square plus uncertainty of density by density the whole square. Then for diameter, then you have for g, and then for head. So by substituting the values, you will get 0.00625, 0.00, which has been found by the previous part A of the question. We have found out all the relation for here. So when you substitute that and square the terms and with respect to adjacent coefficients, you then square each of the terms, sum it up, and then the square root of that will give you 0.005375. So the uncertainty in CD is plus or minus 0.005375 into CD, and CD value we already calculated, it's 0.641, so that will give you 0.00345. So 0.00345 divided by the CD value into 100 will give you 0.5375. So that is close to 0.54. So the answer is option A. So moving on to the next question. We have a dynamic performance of a mercury in glass thermometer, which is prescribed by the following differential equation. So we have to find a dynamic performance. The performance of a glass thermometer is given, and we have to find out a time constant in seconds. A time constant is a constant which in seconds, which is we have to find it in seconds. So your options A, B, C, D. So if you see, this is a first order system. This equation is a first order system. If you remember, it's a dqo by dt plus AOQO equals BOQI. So there's a first order system. You can solve that. You'll have basically it's you have to find out the lambda value, the time constant, and the next also a link question. You have to also find out the static sensitivity. So when you simplify the first order system, if you see the relation between how this first order system is expressed with the given equation, you will get to the time constant and sensitivity. So here time constant, you have options 1.5, 4.5, 3 and 2.5. And we have to also find out static sensitivity. So their options are 0.5, 1, 1.5 and 2. So if you see the dynamic performance, the time constant is A 1.5 and 0.5. So here the equation is 4.5 d theta by dt plus 3 theta o plus equals 1.5 into 10 power minus 3. So what we will do is divide by 3. So we'll get 1.5 d theta naught by dt plus theta naught equals 0.5 into 10 power minus 3 theta I. So when you compare this with the first order equation, the tau d theta naught by dt plus theta naught equals k theta I. Here tau is the time constant, so if you compare it will give you 1.5, and k is the sensitivity, static sensitivity, that is 0.5, 10 to 10 power minus 3. So here we are measuring. So options are 1.5a and b 0.5, which is millivolt by degree Celsius. So moving on to the next question, we have a thermometer which having a first order dynamics. So a thermometer which is behaving as a first order system with a time constant of 1 minute is at 38 degrees Celsius. So we have a thermometer which is behaving as a first order system, and we have also been given the time constant which is 1 minute, and it is at temperature of 38 degrees Celsius. So the thermometer is suddenly placed in a bath at 43 degrees Celsius. So at time t equals to 0, the temperature bath which has to be measured, which is at 43 degrees Celsius, and your thermometer is at 38 degrees Celsius. So at t is equal to 0, you dip the thermometer, and suddenly changing the input is 43 now, and that is it's left there for 1 minute. So time is 1. So you see time constant is 1, and the time is also 1 minute. After which it is immediately returned to a bath at 38 degrees Celsius. So the process in two steps. You take a thermometer which is at 30 degrees Celsius, you dip it in a temperature bath which is at 43 degrees Celsius, leave there for 1 minute, then you remove the thermometer and leave it at the room temperature which is at 38 degrees Celsius, and then at time t equals to 0, what will be the temperature reading? So thermometer gets two types of input. Before at 1 minute you before the thermometer response, it reaches a 43 degrees because the time constant is 1 minute, and then you suddenly take it to 30 degrees Celsius again. So you have options: A 39.7, B 38.7, C is 40.7, D is 41.7. So this is in two steps, you see. So the answer is 39.7. So at e equals to minus 2, when the time constant is 1, it's 0.3678, and so when you substitute the temperatures, you will get T as 39.8 degrees Celsius. When the temperature is at 43 degrees Celsius. So here the temperature it's reached 43 degrees Celsius, and then you are dipping it again, it will give you 39.8 degrees Celsius. Moving on to the next question. When a step input of 100 bar is applied to a pressure gauge, the pointer swings to a pressure of 102.5 bar and finally comes to rest at 101.3 bar. So find the percentage overshoot. So you have a step input of 100 bar is applied to a pressure gauge. The pointer swings to a pressure of 102.5 and finally comes to rest at 101.3. So find the percentage overshoot. Overshoot is how much it is shooting away from the actual value which is to be shown. So that is a overshoot. You have to ask to find percentage. So your step input is 101 bar and your instrument shows that final reading is 101.3 bar. So you first initially after when your pressure, you have a pressure to be measured, you open a valve suddenly and you get a pressure of 100 bar, and to respond to that your initial pressure gauge pointer goes to 102.5 and gradually comes to 101.3 and rests at 101.3. so you have to find overshoot percentage. So options are 1.18, B 1.22, C 1.26, D 1.14. So in this case overshoot is 102.5 minus 101.3. So initial value which it went the pointer reached is as a response it's 102.5, and then at the final steady state value or where it rests is 101.3. so the difference is the overshoot which is 1.2. so make into account it's 1.3 bar from 100 is the error in the measurement. So the overshoot value is 101.3 is the value shown by the instrument. So 102.5 it goes there and comes back. So the overshoot will be the difference between these two and not 102.5 and 100. So 102.5 minus 101.3 is 1.2 bar. So the percentage overshoot will be 1.2 divided by the actual value 101.3 into 100. So it will give you a 1.18% error. So the options will be answer A. Moving on to the next question, we have a certain thermometer has a time constant of 15 seconds. So you have a thermometer, you have a time constant of 15 seconds, you have an initial temperature of 20 degrees Celsius. It is suddenly exposed to a temperature of 100 degrees Celsius. So find the following. You have time to attain 90% of steady state value in seconds. So to reach 90%, how much time it will take? If you have take time constant of 15 seconds to t is equal to 15 seconds, you will reach 63.2% of the temperature which the thermometer is exposed to. So take 15 seconds to reach 63.2% of 100 degrees Celsius. So which will be 100 minus 20, which is 80, 63.2% of that plus 20. So that will be the temperature at 15 seconds. So you have to find what temperature time it will be 90%. So this is a certain thermometer measurement. So it will be a first order system. You have to take a first order system and then solve this. Then also you have to find out the temperature at that above time. So 90% of that temperature that you have to also find out. So in that case the answers are 34.54 seconds and 92 degrees Celsius. So it will take 34.54% to reach 90%, and it will have 90%, 92 degrees Celsius at that temperature time. So the solution, your initial temperature is 20 degrees Celsius and your ambient which is exposed to is 100 degrees Celsius, or which will be a steady state after t equals to infinity, or a large time temperature, larger time when you leave the thermometer to that exposed to that environment of 100 degrees Celsius, it will reach 100 degrees Celsius. So t infinity and time t equals to 0 is t naught, t infinity is time t equals to infinity. So 20 and 100 respectively, and your time constant tau is of 1.5 seconds, sorry 15 seconds. So your time constant is given. So for 90% rise in time, so we have a temperature difference theta by theta naught equals e raised to power minus t by tau. So theta by theta naught is so if you reach 90%, the temperature difference theta by theta naught will be just 10%. So that's why theta by will be 10% of theta naught, So point 1 theta naught by theta naught equals e raised to power minus t by tau. So theta naught gets cancelled. So you'll have e raised to power minus t by tau as 0.1. So when you take a logarithm on both sides, we'll have ln 0.1 equals minus t by 15. So from that it will be 15 ln 0.1, which gives you 34.54 seconds. To reach 90%, then it will take 34.54 seconds. Then at this time, we have to find what will be the temperature. So you know e raised to power minus t by tau is 0.1, which is 10%. There is a difference between that thermometer and the temperature bath is t minus 100. So that difference is just 10% of the maximum temperature difference. It's t naught and t infinity. So 0.1 into 20 minus 100. So that will give you minus 80. So minus 80 is minus 8. 10% of that is minus 8. So 100 minus 8. So you'll get Tt as 92%, 92 degrees Celsius. So the temperature will be 92 at 90%. When it is rise to 90%, it will be 92 degrees Celsius, and it will take 34.54 seconds to reach. So moving on to next question, we have a mercury thermometer which has been on a table for some time. It's registering the temperature. So at t equals 0, it is 75 degrees Celsius. Suddenly, so the environment is at 70, the temperature thermometer is at 75 degrees Celsius, and suddenly you are placing it in a oil bath which is at 400 degrees Celsius. So you have initial temperature T naught is 75 degrees Celsius, T infinity is 400 degrees Celsius. So the following data are obtained for the response of the thermometer. So a table is given which gives you a response corresponding to time, what is the temperature for the thermometer. So the thermometer estimates the time here is given in seconds and temperature is in degrees Celsius. So at 0 is 75, 1 is 107, at 2.5 seconds is 140, and so on and so forth. At 30 it's 385 degree Celsius. So after some another some temperature, it will be 400. It is close to 400. So we have to find estimate the thermometer time constant. We have been asked to find the time constant. So we have to estimate the time constant from here. So we know the temperature value and the corresponding time value. So we can substitute that, and we also know the t naught and t infinity value. So we know theta by theta naught equals e raised to power minus t by tau. So we know theta value. We can take any one of these, and we know theta value. We also know the theta naught value, which is 75 minus 400, and then we also know e raised to power minus t by tau. We know the time. We have to find out the tau value, which is the time constant. So here the answer is 10 seconds. A is 10 seconds, which is 280 degrees Celsius. So the corresponding will be 280 degrees Celsius, which is 63.2% of that. So if you substitute theta naught, the temperature which it reaches equals theta initial temperature is 400, and theta I in is the initial t naught or theta in is 75, and the oil bath temperature is 400. So this is the maximum difference, 75 minus 400 into e raised to power minus t by tau. So if we take temperature at 1 seconds, it is 107. So when you substitute 107 equals 400 plus 75 minus 400 e raised to power minus 1, t is 1 by tau. So 107 minus 400 by 75 minus 400 equals e raised to power minus 1 by tau. So this fraction comes out to be 0.90, and then log of that will give you minus 0.1036 equals minus 1 by tau. So the tau value will be 9.647, which is close to 10 seconds. So moving on, we need to find out there's an arrangement. R is the load. You have any setup or equipment for which we need to find out the power dissipated. So that this is R, the load resistance. So we have an ammeter which measures current, and we also have a voltmeter by E which measures the voltage. So what it says is a resistor has a nominal stated value of 10 ohms plus or minus 1%. So the R value is 10 ohms and uncertainty of 1%. A voltage is impressed on the resistor, so we are suspecting to a voltage, and the power dissipated is to be calculated in two different ways. So the power can be calculated in two different ways. It's E square by R. So we know V equals to E equals to IR. The voltage is equals to current into resistance by Ohm's law, and so we can substitute current as E by R, and we know power as voltage into current, so it will become E square by R. So that, and also knows P equals to E by I, the voltage into current. So in first case only a voltage measurement will be made. So in the first case there is no ammeter, we only find the voltage, while both current and voltage will be measured in the second case. So calculate the uncertainty in the power determination in each case when the measured value of E and I are. So we have to find out the uncertainty when the power is calculated from E square by R relation, and also the uncertainty when power is calculated by E equals to I relation. We have also given the question is given the voltage is 100 volt and the uncertainty is 1%, and the current, for current you have 10 amperes and the uncertainty for the same is 1%, and the circuit is like this. So in this case if you go on, so first case we know we have to use the uncertainty relation. Here omega is the uncertainty, and the dou R by R is the function value which has to be evaluated. So dou by function value by x1 the variable into uncertainty of the variable whole square, the summation of all that raised to power half, the square root of the summation. So here the power variable is the first case it's P is equal to E square by R. So the variables are voltage and resistance. We have uncertainty for voltage given as 1% and resistance also 1%, and the values for voltage and resistance are also given. So when we differentiate power with respect to voltage, we get 2E by R, and when we differentiate voltage with power with respect to resistance, we get minus E square by R square. So we know the differentiated value, and we also know the uncertainties, and when we divide this whole thing by power, the uncertainty of power for relation E square by R will be WP by P equals square root of summation of the uncertainty into the dou P by dou E by P. So that will give you this equation simplifies to 4 into omega E is the uncertainty of voltage divided by voltage the whole square plus uncertainty of resistance by resistance the whole square raised to power half. So if you see the relation is similar to the product relation. If you see, we have product relation that we have the coefficient which E square is 2, so the square of that becomes 4, and then uncertainty which is U by A is 2 for voltage, so that is 4 into uncertainty of voltage divided by voltage plus coefficient of R is 1, and so omega by R the whole square, so that you get half. So after that after the summation, if you substitute the values, it is W is 1%, so of E, so that will be 0.01, and WR is also 1% of R, so that is also will be 0.01. When the square of that so the percentage uncertainty, so WP by P will give you the percentage uncertainty, which will be 2.236%. So the initial case for P equal to E square R being for uncertainty, when you use that relation, is 2.236%. So next case is P equals to EI. In this case you measure both current and voltage. So For this case, we also find dou P by dou E, which will give you I, and power with respect to current, when you differentiate, you will get voltage. When you differentiate this whole thing by P and substitute in the uncertainty relation, we have uncertainty of P by P will give you the same the product relation uncertainty analysis equation. When you substitute into that, so we will have uncertainty of voltage by voltage the whole square plus uncertainty of current by current the whole square, the square root of the summation. So the percentage uncertainty in this case will be when you substitute, both are 1% uncertainty for voltage and current. When you substitute that, we will get 1.414%. So if you see here, the uncertainty is 2.236%, and by when this case it's 1.414%. So there is a difference when you calculate with the different power relation, because the instruments which used to measure are different. So here both current and voltage are used, and here E square is there. So that is making a significant difference in the uncertainty. If you see here, the uncertainty is 4 times. So that will give you. So the second method is better for power determination compared to the first method. So the difference is coming from the relation. So if you see, the uncertainties are same for both the case, but how we calculate that matters, and the uncertainty is different. So second case is having a lower value. So moving on, a similar case, in this case you have a voltmeter which also has an internal impedance Ri, so or Rm. Rm is the internal impedance of the voltmeter. So in this case, the power measurement in the previous example is to be conducted by measuring voltage and current across the resistor in the circuit shown in the accompanying figure. The voltmeter has an internal resistance of Rm, and the value of R is known only approximately. So the value is R is for sake you can say it's not known, because you don't know it for with a certain value. So we know Rm, I, and E. So calculate the nominal value of the power dissipated in R and the uncertainty for the following condition. So basically you should eliminate R from the relation and calculate the power across the load which is being dissipated. So how do that? So we know this current will get splitted between the two resistances, which is I1 and I2, and we know that I1 plus I2 will be I. So using that relation, we will get rid of R. If you see, from current balance we have I1 plus I2 equals I. So then I can be written as voltage by resistance. We know voltage across both are E, because the same voltage is applied. So E by Rm plus E by R equals I. So I1 will be I minus E by R. Okay, so we know I1. Now we can find out I1 value. So I2 value is E by Rm. So substitute I2 value and we can get I1 value. So power dissipated in the resistor is P equals to E into I1, because I1 current flows through across E. So substituting that in I1 relation, so we get E into I minus E square by Rm. So next we have P, which is 500. We substitute the voltage and current values. So voltage is 500 volts and with 1% uncertainty, and current is 5 amperes and 1% uncertainty. Rm is 1000 ohms with 5% uncertainty. So substitute values. We have 500 into 5 minus 500 square by 1000 RM value. So that will give you 2250 watts. So the power dissipated is 2250 volts. We need to find out the uncertainty for this. So dou P by dou E, you see the relation has three variables: voltage, current, and RM, the internal impedance for the voltmeter. So I have three variables. So we differentiate with respect to dou P by dou E, which gives you I minus 2E by RM, then dou P by dou I, which gives you E, and then dou P by dou RM, which gives E square by RM square. So we know three values, three function partial differentiation of the functions with respect to variables. We have to substitute in the uncertainty equation for the power, which will be power uncertainty will be dou P by dou E into uncertainty of E square plus dou P by dou I into uncertainty of I, and so on, the summation of that, and square root of the whole summation. So when we substitute all the values, we will simplify to 5 here dou P by dou E, so I is 5 minus 2 into 500, which is 1000 by RM 1000, so whole square into 5 square, same, then E square into omega I is 0.05, because it's 1% of 5 amperes, so it's 0.05 plus E square by R square into omega R, which is 5% of 1000, which is 50. So the whole square of that, and summation to raised to power 1 by 2, which will give you 34.4 watts. So we have omega P, which is 34.4 watts, and we also know power is 2250 watt. So in percentage in sense, we will give you WP by P is 34.4 divided by 2250, which is 1.53%. So here if you see, the RM has a dominant factor in the overall calculation. You have RM value, which is dominant factor. If you see, if the RM value is very large, here it's 1000, so 1000 ohms. When the RM value is very large, the power uncertainty, it will not affect much. The influence it will have is very small, because it will 1 by RM. When the RM values is close to what the R value, then you will have trouble. Uncertainty values will not be so. Voltmeter, in the previous week also we saw that voltmeter, the requirement is the R value should be very large compared to the load. So that's the requirement same here. You can see the same requirement here. So moving on to the same next question, you have a flow. You have to measure a flow. So you have a flow meter obstruction time, which can be a orifice, venturi, or a nozzle. So a diagram of which has been given. We have used to measure the flow of air at low velocity. At low velocity, you need to find out the flow rate of air, and this is the flow meter. You are measuring pressure and temperature at the inlet, and also the temperature pressure difference between 2 points. And the relation for the flow rate is given as follows, which is m dot, which is the mass flow rate, which is equals to a constant, which is a discharge coefficient, then area A into 2g, g is your acceleration due to gravity, and then you have P divided by RT1, the temperature which has measured, into P1 minus P2, which is the delta P, the difference in the pressures, raised to power half. So the mass flow relation is given, and the variables are mentioned. We are also given that percentage uncertainty of the mass flow rate has to be calculated. So C value, the empirical discharge coefficient, is 0.92 for this case, and you have also plus or minus 0.05% of uncertainty. So this has already been calculated and calibrated, so that value is given. You have pressure gauge here at the inlet, it says 25 psi atmospheric, so that, and it has uncertainty of 0.5, and the temperature, which is gives a 70 degree Fahrenheit, which is 2% uncertainty, and the T1 value is 530 Rankine. So delta P is also given, which is 1.4. So the P2 minus P1, that is already being calculated, P1 minus P2, so that is 1.4 psi plus or minus 0.05 psi. And there is also area which is given as 1 inch square plus or minus 0.01 inch square is the uncertainty for the area. So the area uncertainty is directly given. The previous case where we saw a flow meter, there the diameter was given and we calculated the relation. So here which is 2 times the diameter uncertainty by d. Here it's already given. So if you see, mass flow rate is a function of empirical discharge coefficient, area, pressure at the inlet, the pressure difference between the two, the throat and the inlet, and then the temperature at the inlet. So we find out the corresponding partial differentiation for with respect to the variables for the mass flow rate. So we have dou m by dou c for the discharge coefficient, which is a by 2 gc p1 by rt1 into delta p raised to power half. The mass flow relation equation is already given. You have to just differentiate that, and we know also the relation with respect to area, so that is also known. Then differentiate with respect to p1, which is 0.5 ca into gc by rt1 delta p raised to power half into p1 minus half, so that is also known. Then we differentiate with respect to the pressure difference delta p. So P2 minus P1 minus P2 is the delta P denoted as delta P, and dou m by dou T1. So we get another relation for that. Next, what we do is differentiate the divide the whole thing by mass flow rate, and then it's just same as the product relation. So for uncertainty, you substitute that, and with respect to the coefficients and the uncertainty by the variable. So you have Wc by c the whole square plus Wa by a the whole square plus 1 by 4 Wp1 by p1 the whole square plus 1 by 4 W delta p by delta p the whole square plus 1 by 4 Wt1 by t1 the whole square into raised to 1 by 2. So we have all the coefficients here. So when you substitute the values given, so we have all the values, so we have to just substitute all the values here. We know all the uncertainties and the corresponding values. So we take 0.005 by 0.92 whole square plus 0.001 and so on and so forth. We substitute all the values, and so we get 29.5 and 10 power minus 6 1.2. So this the summing up all and raised to power half will give the percentage uncertainty in the mass flow rate measurement will be 1.172%. So we have found out the uncertainty for that. So next, when we see, we have a temperature probe which was heated by immersing it in a boiling water, and then it was quickly transferred into a fluid medium. So at a temperature of ambient T amp is 25 degrees Celsius. So a temperature probe is you have a boiling water. We have already kept the probe in that boiling water, and so the temperature probe would have reached the boiling water temperature, and then we are transferring it to a fluid medium at temperature of ambient. So we are taking that out at the ambient condition of 25 degrees Celsius. So the temperature difference between the probe and the medium is recorded. So probe is at initially at some temperature, and then you have ambient temperature. So the difference between that is T minus 25. So that has been recorded for different time, and that has been reported. So 0.35 you have a 60 degrees difference, temperature difference. Then 0.6 you have 50 degrees difference. Then 0.937 you have 40 degrees difference. And then 1.438 30 to 0.175 20. At 3.25 you have 10 degree difference between the temperature of the probe and the ambient. So in this case, what is the time constant of the probe in this situation? Previously we have the same, this thing there we solved it by a different approach. where we took some time, and then we took that was the easier approach. You can solve it by another different method also. If you see how that works, there we didn't use all the data. If you see in the previous case, here we have a set of data, but we used a single data. We didn't use all the data, because we just used time equals 1 second and that corresponding temperature of 107, and using that we estimated a time constant. It's the question is similar here. You see, the question is similar here. So, and here we are what will we do is we'll fit that data. So here we are assuming that this will be a straight line. If you take a logarithm of the temperature, if you see the relation is theta by theta naught equals e raised to power minus t by tau. So if you take logarithm, so it will be ln theta plus ln theta naught minus t by t star. So this, if you see, that's a linear relation. So if you take a linear relation between logarithm of the temperature difference and the time, we can fit a data. So when we employ least square method, in the least square method, if you see, is minimizing the summation of y minus yi the whole square. So we have some y value and we have the data value yi square. We have to minimize that. So the line which your curve fitted and the data value, you should minimize it. So yi, you substitute that axi minus b, you assume y equals ax plus b, and then the whole summation of the yi y minus yi the whole square, the summation of that you have to minimize that. So in case of minimizing, you have two variables. You have a and b for the data. We are assuming a linear profile. You have y equals to ax plus b. So you have y equals to ax plus b. So a and b are constants which has to be estimated to know the curve or the line which passes through the data which has been fitted. So using least square, y equals to y square yi square. So you differentiate that, substituting y equals to x I minus b. With respect to a and b, you get two relations. You will get two relations for dou. If you say function f is summation of y minus yi the whole square, you have dou f by dou a. So that will give you one relation, and dou f by dou b will give you one relation. It will come out to be summation of yi equals a summation of xi plus b n, and same another will be summation of xi yi and so on. So you can solve it simultaneously, or you from the lectures you will know you can have a relation for a and b. So using that we can find out the constants. So in this case you have ln t minus t ambient, which is the y. So y equals to a is minus 0.6065 and b is 4.2837. Since 4.2837 is ln of theta naught. Theta naught is the maximum value which can have. So that in this from the data for the curve, this is 4.2837. So we don't know the actual temperature at which the thermometer was there, but it will be fairly close to 4.2837. So if you see r square value, the fit, how good the fit is, which is 0.9989. So if you, this is fitted in Excel, if you see this is similar, so 0.9989. So we have 4.2837 minus 0.6065. So if we have the relation t minus t infinity by t naught minus t infinity equals e raised to power minus t by tau. If you take a logarithm of this, we will get ln t minus t infinity. T infinity is ambient, so ln t by t minus t ambient. So that is there, minus ln t naught by t naught minus t infinity will get. So if you take that to the right hand side, that is equals to 4.2837, and then we have minus t by t star, t by tau. So we need to find tau. So we have minus t by tau is minus 0.6065 t. So that, so tau basically we can find it by minus 1 by slope. So here the slope is minus 0.6065. So either that, or you can take a logarithm of the relation for temperature with respect to time, and then you can compare that and you can take tau. So from there tau will be 1.0.6065, which will come out to be 1.65 seconds. So that is the time constant. So that's all for the today's class. Questions? So thank you. In this case, if in this case, if we see by approaching the previous example, if we substitute t is if you substitute t is 30, so if we substitute t is 30, you can solve the previous example, but here we don't know the actual temperature. That's the case. If you then we have to substitute for two examples, and then we find out t uh, and the time constant. We have to find two equations and then solve by trial and error. That can also be done. And but the simpler best way is to do is fit the line, and then from the slope we can directly find out the time constant. Thank you. That's all for today's class. As no one has doubts, we'll close the session.